Scott Hotaling from Utah State University in the US. Over to you, Scott.
Hey everyone, let me figure out getting this shared properly. All right, you should be able to see my screen.
Yes.
Yeah, so this is a really cool event to be part of, and I appreciate the invitation. And it's been really great getting to see so much other work of, people that I don't necessarily know personally, but I've known of the things you're doing for a long time. So the Faces with Names part of this has been really great. I'm going to talk about something that I don't want it to come off as dismissive of what's happening to mountain glaciers around the world. Certainly, like the change and decline in surface ice glaciers, as I'll talk about them, is a huge deal, and the impacts of that are really tragic and concerning, and there are just so many words for it. But I thought it would be interesting to talk about some more resilient ice types around the world, or at least the work we're doing to try to understand if there is more resilient ice around the world, and specifically these features called rock glaciers, which are something that I've been working on for about 10 years now, although increasingly from a physical standpoint, although it used to be almost purely an ecological and water resource standpoint. So I'm a faculty member at Utah State University in the Western US. So as we've seen many, many examples of, glaciers are changing around the world. They're changing really fast. These repeat photos are some of the most amazing ways that I know of to really connect people to landscapes. These are all places in the Western US. So just to add those to the European and Indian perspectives and Himalayan perspectives that we've been seeing, but it's just the story is the same. It's basically, whatever, especially in the temperate regions, wherever you look, you see massive decline and an ongoing trend towards deglaciation, which is a incredibly concerning word to throw around given the mountain landscapes and how they impact not only the places that we love, but actually the resources that we depend on. And obviously the central theme in all of this is a rapidly warming planet paired with more precipitation falling as rain instead of snow. And so I just plotted the data from snow telemetry sites in Utah, the state I live in, just to look at overall trends and the amount of peak snowpack, and then looking at different regions in the state. So overall, we see about a 16% decline in Utah's snowpack since we started carefully measuring it in 1979. And we have a bit of a stronghold of snowpack in the northern, especially higher elevation part of the state. For those of you that are familiar with the US geography, the Wasatch Mountain Range, which is a very famous area for skiing, is essentially the place where snowpack is declining the slowest. But Utah is a very diverse state. We have red rock deserts that are surrounded by high mountains that still get a fair amount of snow in the winter. And those more southern latitude, warmer areas are seeing the fastest rate of decline. So the highest elevations down there have seen about a 22% decline. And they're currently at about, I think, 50% of normal snowpack for this time of year. So that trend is not reversing anytime soon. And all of this shapes this paper that I really appreciated about 4 years ago by Cyrilia Woodburn and colleagues, of this low to no snow future, where snowpack, we're going to experience this transformation in the Western US, and I'm sure elsewhere in the world, where snowpack doesn't accumulate in the way that it used to. And that obviously creates massive changes to how water is stored in mountain systems, how glaciers, like the health of glaciers and their long-term trends and everything else. And so that brings me to where we've been focusing a lot of attention, is on these features called rock glaciers. This is a rock glacier that I work on in Idaho, which is a little bit north of where I live. And then there are a couple more that'll come through. And so these are big masses of debris covered ice. Maybe this is just the Idaho rock glacier, so I'll skip on. So these are large masses of debris covered ice. They have all of these defining features, which are very reminiscent of glaciers. I mean, they're essentially an ice mass moving under debris. And so they have this steep front. They have this furrowed ridge topography where it's almost like a melting ice cream cone. And it really just kind of highlights this underlying nature of ice. And they either flow downhill and contain ice currently. Those are often called active rock glaciers. They contain ice, but they no longer flow. Those are inactive, or they don't contain ice nor flow any longer. And so the feature will still be there, but it has been depleted of its internal ice. And those are relict rock glaciers. And so these features are incredibly common around the world. They're not as common as mountain glaciers. David's talk gave us a great number of, I think, 315,000 glaciers outside of the polar ice caps. This inventory by Jones et al., which also synthesized other studies, I estimated there are about 51,000 rock glaciers, and of those, about 28,000 actually still contain ice. In my home state, there are 800, which is very surprising to people that live in Utah, considering there are no surface ice glaciers in the state. So people don't actually think there's any perennial ice in this state, but there's actually a lot of it. And it's concentrated in our highest and biggest mountain range, the Uinta Mountains, which are fairly unique because they run east to west. Rock glaciers contain significant ice. Obviously, this ice is a much smaller version of the ice amounts that it's contained in the bigger glaciers we've talked about so far. This is a place that I work a lot called White Pine Lake in the Wasatch Mountains. If you can see my cursor, there's a rock glacier up here. There are about 4 rock glaciers in this basin. And this reservoir, which actually is used for agricultural supply in Utah, is 100%, as far as I can tell, fed by rock glacier melt in late summer. So the rock glacier is pretty important to that water resource locally. And then these are some photos of rare exposures that we found where we could actually see the internal ice in the rock glacier. Typically it's covered by debris, but these are spots. These photos on the these two right-hand photos are actually from the right-hand side of the rock glacier about 3 years ago. And if you look around the world, the Jones et al. Paper also made an estimate of the water volume equivalent in all of these rock glaciers. I have a feeling, I haven't talked to the authors about this, some of them might be on this call. I have a feeling they would agree that this was a rough first pass estimate. It's extremely hard, as you might imagine, to estimate how much ice is in a rock glacier, even in one individual basin, much less doing this globally. But we're pretty confident, we can be pretty confident there is a fair amount of ice in these features. And these features support cold water biodiversity. And the climate refugia component is one of the, I think, most important and fairly overlooked so far in the biodiversity side of the research community. And so we wrote a paper about 4 years ago now, highlighting that these rock glaciers and other, ice-filled talus slopes and things like that could be really important climate refugia for mountain biodiversity. Essentially, as a landscape loses its surface ice, if this subsurface debris-covered ice persists and still supports, streams and wetlands and things like that, then that cold water biodiversity in the region will not be lost. It'll just be reduced to a smaller, more sparse distribution. And so some of the species that will be impacted by this are things like this meltwater stonefly. This is actually an endangered species in the US due to climate change induced glacier loss. And so Lednia lives in the meltwater of rock glaciers. And then plenty of salmonid species require cold water, and they can live in some areas because there are rock glaciers supporting cold water conditions that otherwise wouldn't exist. And I'll show you some temperature data in a few slides highlighting that if you take away some of these perennial ice features in a basin, streams warm extremely rapidly. And so the kind of meat of this talk is that rock glaciers appear to be resilient to climate change. How resilient, how long they're going to persist, these are very, very open questions. But at least so far, I'll show you a couple examples of the data that supports this resiliency. So this is a study from the French Alps from authors that many of you have a better chance of knowing than me. I have not been able to personally meet them, but I really like this paper where they went out and over 70 years, they did repeat surveys of this rock glacier in the French Alps. And what they essentially showed was from 1952 to 2019, it largely didn't change. And that's relative to surface clean ice glaciers in the same region that lost quite a lot of mass. And so I add a rate of recession. Obviously, that's their mass balance essentially goes through zero. So that could be any number. But the basic idea and the basic result is that this rock glacier largely didn't change while surface ice glaciers receded in the same basins. And we're confirming this and seeing similar patterns in the US. So this is data from the Teton Range in Wyoming, which is a place that I work a lot. This is a collaboration that's been led by Dan McGrath's lab at Colorado State University with Ash, his PhD student, doing some amazing physical science remote sensing work. And essentially what we have is repeat LiDAR data for an entire mountain range from 2014 and 2022. So we can take that LiDAR data and difference it on a pixel by pixel basis and essentially say, at this point in space, what has the vertical change been over that 8-year period? And so this is the 11 named glaciers in the Teton Range. The scale, dark red, is upwards of 15 meters of vertical ice loss. So essentially they are all red, which I'm sure every single person on this call would not expect anything less. But the really interesting part is when we start looking at the 50 or so rock glaciers that are interspersed throughout the same basins, same aspects, same elevations as these surface ice glaciers. These are some examples of the rock glaciers. Obviously much lighter red, seeing much less change. And even some of these places where there's like a little bit of dark red along the margin of a rock glacier, we've cleaned up some of these boundaries a bit better because those are actually perennial, like small perennial ice fields that are exposed at the surface and are responding very similar to glaciers in the region. Just to summarize this, the rock glaciers are losing 0.05 to 0.08 meters of ice, or at least they're changing 0.08 meters vertically each year, whereas the glaciers in the same basins and area are losing more like 0.7 meters of ice vertically every year. And so when we translate that to stream temperatures and actually look at what are the impacts of ice loss in this region on cold water habitat where endangered species or others live, we first see that glaciers are doing a good job of buffering stream temperatures against warming over, this is a 2015 to 2024 period when we've been monitoring many of the same streams in that LiDAR data set with continuous temperature logging. Obviously, how long this buffering will last when you're losing 0.7 meters of ice every year and glaciers are maybe 20 meters thick is a pretty open question, but we can kind of imagine where that's going. Rock glaciers are acting similarly. They're essentially haven't changed over this record, and they maintain this cold temperature, and the scale of temperature is the same across all three plots. Where we really see a very concerning trend is in basins that don't have a glacier nor a rock glacier. They are warming extremely fast in the Teton Range on the order of like 0.5 degree centigrade per year. And so for now, the snowmelt loss is the big kind of driver of this warming. But I expect as we continue this record, as these glaciers get smaller and smaller, their buffering capacity of stream flow temperature will be reduced, and eventually these rock glaciers will be what persists. So these rock glaciers are poorly understood. There are a lot of questions that remain. The three big ones are just how much ice do these features contain around the world and water? What is their environmental and geochemical influence on downstream systems? This will become increasingly important as they become a more dominant water source on the landscape. This is a pressure gauge that we've installed in the high Teton Range below a rock glacier. And then how are they going to support climate refugia into the future? And so I want to conclude with a short advertisement. This past summer, my students convinced me to finally start a YouTube channel about the work that we're doing and about climate change and mountain systems. And the point of this largely is to do what I think a lot of us are, like this whole event is doing, and events around the International Year for Glacier Preservation and other efforts, is that we can publish amazing science all we want, and that can be in journals, and it's really, really important, but we have to also connect that science to people and give them a connection to it, to see the people doing the work, hear about the issues. And that's the way we really make a difference in terms of changing behaviors and stopping carbon emissions globally. And so we've been really excited about the trend and the subscriber growth and interest in the channel. We'd love for any of you to check it out and share it with people you know. My students literally send me Slack messages whenever someone subscribes, which is very cool. And then increasingly, or most recently, we've started actually interviewing mountain scientists about their work. Again, to try to put that human face to, the changes that we're seeing in the world, and also just to tell the stories of the actual scientists doing the research. I've noted many names in this group of people to potentially reach out to for one of these chats. And so we basically do an interview and then add in, context to that. So, and so this was an interview that I did with Eric Gilbertson, who has been tracking the actual shrinking of ice-capped mountains in the Western US. So please reach out if you're interested at all in that, and I'll put a link to the channel in the Zoom chat. So thank you.
Thank you, Scott. That was really fascinating. I guess the only solution to glacier preservation is to bulldoze mountains of rocks on top of the ice to
Yeah, I mean, engineers asked me about, like, could we create rock glaciers, or could we blast and get debris onto existing glaciers? And like, while I don't think that's a great solution, I do think we need more people thinking of those kinds of ideas that are maybe a bit outside the box.
Okay, and I noticed that you